This is section 6.2 on theoretical and experimental probabilities and the law of large numbers. Start out with some vocabulary. Make sure you copy these down. The theoretical probability is the probability of an outcome occurring based on probability principles. And this is in contrast to an experimental probability, where the probability that a certain outcome will occur is determined through an experiment. So the theoretical probability is where we use math theory, and experimental probability is where we perform an experiment to find out the probability. Finally, the law of large numbers says that as the number of trials, or randomly drawn observations in a sample, increases, the mean of the sample gets closer and closer to the theoretical mean. Copy those down and we'll take a look at what this actually means in practice. Here's a quick thing to read here. When all possible outcomes are equally likely to happen, you can find the theoretical probability of an event without doing an experiment. For example, flipping a coin. If you flip a coin 10 times, you'll find the experimental probability of getting a heads. Experimental probability is performing experiments and observing the outcomes. If the experiment is run an infinite number of times, the law of large numbers says that you'll get closer and closer to the theoretical probability. So the more you do an experiment, the more you'll get closer to the theoretical probability. Math traditionally uses theoretical probabilities, and the sciences traditionally use the experimental probabilities. So let's decide which one is theoretical or experimental. 2 dice are rolled. What is the probability the sum will be 12? Well, we don't actually need to run the experiment to find the probability, because we can use what we know about a 6-sided dice and know that there's a 1 in 6 chance that a 6 would come up. And so, before we go into the math, we're just going to say that this is theoretical. You draw a picture, use the math to figure it out. Next one. A baseball player has 126 hits and 410 at-bats this season. What is the probability he gets a hit in his next at-bat? Well, there's no math theory that's going to be able to tell me how many hits a player is going to get in a season. But if we observe this player and take a look, we could calculate their average. So this would be experimental. Next one. A bird watcher observes that 5 out of 25 birds in a garden are red. What is the probability the next bird to fly into the garden will be red? Again, there's no math that would theoretically be able to predict before we observe the birds which ones would be red, so this is experimental. The bird watcher had to do the observation first before we can calculate a probability. And then finally, a hand of 2 cards is dealt from a standard deck of cards. What is the probability that both cards are clubs? So you remember from the last section, we could do that without actually running this experiment hundreds of times. We could just know that since there's 52 cards in a deck, that we can calculate this with math. So now let's do some of these theoretical probability problems. Find the probability of rolling a 2. That's what P of 2 here means when a fair die is rolled. Well, the probability of rolling any particular number on a die is 1 out of 6. So the probability of rolling a 2 is 1 out of 6, or 1/6. Probability of rolling a 1 or 6, P of 1 or 6, when a fair die is rolled. Well, we need to find the probability of 1 and the probability of 6 and add them together, because there's OR, and 1 and 6 are mutually exclusive events. That means they can't happen at the same time. You can't have a 1 and a 6 at the same time when you roll one die. So the probability of 1 or 6 is equal to the probability of 1 plus the probability of 6. We know that each of those there's a 1 in 6 chance of happening. So we add those together to get 2/6, which reduces down to 1/3. Next one, 2 dice are rolled. What is the probability that the sum will be 12? Well, as we started to talk about earlier, the only way to get a sum of 12 when you roll 2 dice is to have a 6 and a 6. So we need to find the probability of a 6 and getting a 6. So we'll take probability of 6 times probability of 6, because whenever we have 2 separate events and we want to know the probability that both occur, not or, but and we multiply. And each of those has a 1 in 6 chance of happening, so you multiply them together and you get 1/36. Now let's go on to experimental probability. Suppose there are 2,000 students in your school and 1,158 of them are female. A reporter for the school paper chooses a student at random to interview for the next issue. What is the probability that the student chosen is a male? First, we need to figure out how many males there are. So if we have 2,000 students and 1,158 females, we can subtract to calculate that there are 842 males. Then we need to take that 842 out of the total number of people in the school to find the probability. So if we look up above, we have number of times the event happens over the number of times the experiment is done. So the number of times that a male would happen would be 842, and the number of times that we could get a person is 2,000. So to calculate our probability, we would go 842 divided by 2,000. And there's two ways to leave your answer. You can leave it as a decimal or a fraction. Typically, when you do experimental probabilities, it's left as a decimal, and theoretical probabilities are left as a fraction. But in this case, you could leave it as either. A baseball player has 126 hits and 410 at-bats. What is the probability he gets a hit in his next at-bat? Let's take the number of times he succeeded and got a hit, that the event happened, out of the number of trials. So 126 divided by 410, and that is going to give us 0.307. You'll notice that when you leave your probability as a decimal, it's always going to be somewhere between 0 and 1. If you're leaving it as a decimal and you get something that's negative, or you get something that's larger than 1, you've made a mistake. You'll also notice that if you follow baseball, when someone talks about someone's batting average as being 300 or batting 307, this is what they do. They divide the number of hits into the total number of at-bats, and they calculate this probability, and they leave it at 3 decimal places. Finally, example C, a bird watcher observes that 5 out of 25 birds in the garden are red. What is the probability the next bird to fly in will be red? We're going to base this probability off of our previous observations. So we're going to say the probability of getting a red bird is the number I observed, 5, out of the number total observations, 25. So in the past, 5 out of 25 were red, and as a decimal, that's 0.2, or as a fraction, it would be 1/5. Now the law of large numbers. Here are a couple of graphs that show what this means. So let's say you are flipping a coin. The first flip might be heads. The second flip might be heads, and then if you only did 2 flips, you would say, well, there's a 100% chance of getting heads. But if you kept flipping the coin over and over and over, the probability that you'll get will probably kind of fluctuate up and down a little bit, but in the long run, after you run, let's say 100 trials, it's fairly close to 1/2, which makes sense because you would assume that you have a 50% chance of getting heads or tails. And here's the graph that goes even farther. So this one goes to 1,000. And again, it's not perfectly in the center, but it's pretty close. And what the law of large numbers says is that the more times you do it, the more likely you are to end up very close to your theoretical probability. So if the population is large, the estimate for the population mean is better than if it's small. The sample mean is a good estimate for the population mean, as long as the size of the population is large. And if we increase our sample size, if we ask more people a question, or if we flip the coin more times, or if we watch a batter take more at-bats, something like that, the sample mean will be a better estimate. So we'll be able to have a better estimate for the mean, or the average. Here's an example. We wish to estimate the mean price of all hotel rooms in Las Vegas. The Convention Bureau did this in '99 and found a sample of 112 rooms. In order to get a better estimate of what the actual mean price is, what should we do? Should we take a larger sample, because then the mean will be closer to the actual price? Yes, we should. That is true, because the law of large numbers says that as we get a larger sample, we'll get a better information. Should we take a smaller sample, since we'll be less likely to get outliers? No, we should not take a smaller sample. We're less likely to get any particular outlier, but overall we'll get actually much closer to the average, and those outliers will be factored out. And finally, if we take a different sample of the same size, since sample size doesn't matter, well, we already decided that sample size does matter. The larger sample will help us get closer to the actual price. So again, that is false.